Good morning again, everyone. Today we are going to continue and finish chapter 3. We are going to see three more families of distributions, discrete random variables: geometric distribution, negative binomial distribution, and Poisson distribution. Meanwhile, the homework is out. You have about 10, let's see when the deadline is. I think it was. So yeah, the homework is here available, and you have about 5 days until the deadline. The deadline is this Sunday. So you'll have the weekend to work on it. It's not a very difficult homework. A couple of exercises similar to the ones in the quiz. And also we are going to have our third quiz this Thursday, again available until Friday, and it's going to be about this chapter 3, the family of distributions. All right, so last time we have talked about how we use these tables to answer problems related to probabilities, and the distribution tables are given to us as cumulative distribution tables, meaning that they give us basically the probability. This color is, each time it's random, I think. No, it's, can I change the color to something else? No, it's yellow. It's really bad. Oh, maybe here there's an annotation menu somewhere. Where is it? Yeah, right here. It's on the left hand side. Okay, so I can also change the size, I think. No, cancel. This is line, this is pen tool, pencil tool, text tool. Anyway, yeah, this one. You may select pencil. It's thinner. I like this way better. So what was I saying? So when we the CDF, the cumulative distribution function, is giving us the probability that our random variable is less than or equal to some given value x. Okay, so this one is given in the cumulative distribution table. But if you're looking for an interval, or if you're looking for a specific variable, for example, and this probability, for example, CDF is sometimes we refer to CDF as by writing the distribution or underneath as a subscript, or maybe superscript, but most of the time, for example, CDF, binomial, and we also write its parameters here. For example, in the binomial distribution, there is the probability of success and the number of trials. If you remember binomial distribution, the names may be confusing at first. I mean, what was Bernoulli, what was binomial? Just as a reminder, Bernoulli was that single experiment that you try with a success probability P, that's the only parameter. Binomial is an extension of Bernoulli to extension of trials to n trials. So it has two parameters. For example, if you want to get in 10 trials, 0.3, okay, is the success rate. So we write the parameters here, and when we write, for example, the binomial CDF5, this gives us the probability to obtain to obtain 5 or less successes in 10 trials when the success probability is 0.3. Okay, so if we wonder about what is the probability of obtaining exactly 4 successes in 10 trials in this probability, with this success probability, we simply, if you're wondering about exactly 4, you need to subtract CDF3 from it to figure out the probability of obtaining exactly 4. Okay, so since you can do this in discrete random variables. Okay, when you have a discrete random variable, you may be asked about what is the probability of exactly obtaining 4 successes in 10 trials, And you can use this cumulative distribution tables, CDFs, and sometimes, as I said, we write which CDF it is. It's the binomial with these parameters underneath it as a subscript. But if we have continuous variables, we cannot use them. We are not going to be asking point probabilities in continuous random variables. We will be asking intervals, probabilities of intervals. For example, what is the probability that the lifetime of a light bulb is between 3 and 4 days? In that case, we will be referring to an interval, and again, we will be using this exclusion-exclusion principle to figure out, for example, you're going to get the CDF of 5, for example, if it's been 3 and 4 days, CDF 4 minus CDF 3. This time, if this was a continuous random variable, it will give us the probability of the lifetime of a light bulb between 3 and 4 days. One thing that is interesting in continuous random variables is that it doesn't matter whether you include the boundaries or not. All right. For example, if because probability of obtaining exactly 3 is 0, right? Whether so in this one, let me write it here. Probability of x less than 3 and probability of x less than or equal to 3, not p, x, I wrote it incorrectly, x less than or equal to 3, these are equal to each other in the case of continuous random variables. Okay, when we have continuous random variables, whether you include or exclude the exact boundary you're looking for, it doesn't matter because it's a single point. The probability of x is equal to 3 is 0, and therefore whether you include 3 or not, the boundaries does not matter. In the case of continuous random variables, again, I repeat, this is really important. This will make a huge difference when this is not equal to each other in the case of discrete random variables. In the case of discrete random variables, this may be the probability of x is equal to 1 plus x is equal to 2, while in this case it's going to be x is equal to 1, 2, or 3, which may be totally different. I will stop annotating now. All right, so let's go ahead and quickly talk about the remaining distributions in this chapter. And some of these distributions are really related to each other. For example, geometric and negative binomial, and binomial, everything is actually related, except maybe Poisson. Poisson is different, and its parameter is different. It's like the average observed event in a fixed time interval. The only different thing from these distributions are Poisson, but all the others, for example, binomial is a number of Bernoulli trials. And so a geometric distribution is the number of trials to do until first success. So again, we are doing some binary trials. In all of them, we are making some trial with some success probability, and we either look at how many successes we have, that may be the unknown thing, or the successes may be given, and how many trials we have. So it's either we are looking at the number of trials or number of successes, and it's either 1 or k. So these are the differences between 4 discrete distributions we're going to talk about. So I'll get to your question now. For discrete random variables, PDF and PMF are the same. Yeah, we actually use the term PMF for discrete random variables, but sometimes in some books or even in MATLAB, for example, you see that the PMF is referred to as PDF, probability density function. So probability density actually, in order for something to be density, I think it has to be continuous. It has to be integratable. Or you should be able to take the derivative. These are, in the case of discrete random variables, our probability density functions are step functions between intervals. So they're not continuous. So you can not take their derivative, but therefore, to refer to them in the most correct way, we have to tell them probability mass function. Okay, so we should refer to discrete random variables distributions as probability mass function, but sometimes when you see they are referred to as probability density function, that's okay. So you're going to understand they mean the same thing. All right, so there's no in the true sense, discrete random variables, there is no PDF. Okay, we shouldn't talk about PDFs. So therefore, the question, are they the same? Is just, I mean, PDF doesn't exist for discrete random variables in the true sense. But when somebody's talking about PDF of a discrete random variable, they are actually referring to the probability mass function. Yeah, here what we have found, here is the PMF for discrete random variables is PMF, but sometimes they are referred to as PDF. All right, so this is just maybe sometimes the distinction between discrete and continuous random variables is also not like black and white. There may be some discrete variables that you treat or approximate by using continuous distributions. We'll see an example of that actually, and for that we have to be very careful about these boundaries. We may need to do some correction if the probability that we're asked is about these boundaries. So we have to take in, we shouldn't forget that discrete variables are always there. Probability mass functions are like step functions, or I mean, the CDF is like a step function, always increasing or non-decreasing. But their PMFs may be decreasing, increasing, but they are not continuous. We should take into account when we are solving these. But as I said, sometimes we use continuous distributions to approximate when we are asked something about a discrete distribution, especially when that in binomial, for example, we are going to see that when n is large, more than 30, the number of trials is more than 30, there's a normal continuous distribution, a normal distribution can be used to approximate the binomial. Because when the numbers get large, you cannot compute the probabilities exactly anyway because of precision limits of our computers. But as I said, in this when you're reading this chapter, these are not different families of distributions. Bernoulli binomial is related to geometric. Geometric is related to, so geometric is a specific case of negative binomial. And the term negative binomial actually should be correctly stated as inverse binomial. There's nothing negative about it. It's like the inverse binomial. For example, in binomial, what are we asked? What we don't know is the number of successes. Okay, so the given input parameters to the distribution in binomial is number of trials, and in other words, they're fixed. Number of trials is fixed, and the success probability is fixed in binomial. We say, for example, we toss the coin 10 times, and the probability of getting ahead is 0.5. So these are two fixed parameters, and then we ask probabilities about what is the number of heads. Okay, so this is the binomial. Now, imagine we reverse the role of the trials and successes. Now, we are given what we fix here is when we fix the number of successes. For example, I want to get 6 tails. All right, I want to get 6 tails. And this is an unfair coin. The probability of a tail is 0.3. How many now? The fixed thing is the number of tails and the success probability. The probability. What is when we think about the number of trials to get exactly that many tails? For example, what is you can see, for example, if you want to get 6 tails, the random variable has to be at least 6. So it's going to be something between 6 and infinity, because the getting all heads all the way until infinity is a non-zero probability. So we may be very unlucky that, I mean, if your goal is to get 6 tails, you may get head all the way 100 times, 120 times. So starting from 6, it may go all the way to infinity. But as you can see here, we will be asking probabilities about what is the probability to try 50 times or at least 50 times to get 6 tails. What is that? So we will, if we change the role of these two things, the successes and number of trials, we fix one of them and ask probability questions about the other, the binomial becomes a negative binomial. As I said, it should be like more immersed binomial, or yeah, it's like the success and number of trials, they change their roles only, and it becomes a different distribution. And geometric distribution, what we're going to see right now, is a specific case of negative binomial in which we're looking for the first success. Okay, the number of successes is fixed to 1 in geometric distribution. So negative binomial is a generalization of that when we want to observe not just one success, but k successes. Okay, so this is how they're related to each other. And Poisson is also related to like geometric. It's like the waiting time until the next success. We can, it's not like that. Sorry about this. So it's the exponential distribution is about waiting times. Poisson is like, Poisson will be related to exponential distribution we are going to see, because when you talk about waiting time until the next event, it's something continuous. Right now in this chapter, we are talking about discrete random variables. So we are counting things, number of trials, or number of, number of trials is like if you conduct each trial at a specific frequency, every minute you conduct a trial, for example, then the waiting time until the next success is going to be like a discrete time, and which is measured by number of trials, but you can convert it to minutes if you want, but it's still going to be discrete. We are going to see that in exponential distribution, for example, we will be looking at things, the continuous time, and Poisson distribution, which is about, for example, there are 5 accidents on the average in a day in Ankara. That's kind of a variable, is a Poisson variable. When we talk about average number of events in a fixed period of time, like 5 accidents in a day. We will be asking about probabilities, like what is the probability to observe 3 accidents this day today in Ankara, or what's the probability to observe 8 accidents that day in Ankara if the average number of accidents is 5 per day. So that's basically Poisson distribution. So I just summarized all the distributions that we are going to see today, and let's go into their details. And there are some nice examples about these distributions, and they have interesting properties, and we are going to talk about those until the end of the lecture today. So geometric distribution is an interesting distribution in which its support as infinitely many integers, which means that the values that the random variable can take is from 1 to infinity. So you can ask probabilities about what is the probability to get the first success in 1,000 trials. It may be a very small probability, practically 0 for all our purposes. So although we say all the way to infinity, it's possible to all the way to infinity, but probability of observing such a large random variable will be very, 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 very low. So here is the probability mass function. It has, again, it says just one parameter, okay, because the success probability, because the number of trials is the random variable itself. So if you look at what this is saying, the number of Bernoulli trials needed to get first success. So the number of successes is fixed to 1, and the number of trials is the random variable. Here, the only parameter that the geometric distribution has is the probability of success, which is that p. Now, let's go back to here. The probability of one success. We are going to do n trials, all right? And we want to have one success. N is actually, we don't know, the trial is not fixed. We are going to do a number of trials, and we want to get one success in this number of trials. So can you tell me why, for example, this is success. Let's write the failures and success. Okay, failure, 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 and one success. So this success actually could be in different places, right? The success could be here. The success could be here. Why don't we have the combinatorial, the combinatoric in this PMF? Why don't we have this? Why don't we multiply this with X? Because it could, if I'm going to do X trials, if X is the number of trials, success could be anywhere within that number of trials, right? Why is the probability like this, the probability mass function? The probability to get a success in X trials is P times Q to the power X minus 1. So is this telling me something? So actually, this is a trick question. Yeah, we don't get exactly. It's so you get it correctly immediately. So this X cannot be in, the success cannot be anywhere, right? So you answered this trick question correctly. Let me get back to this one. So after the first success, we don't care about the remaining trials. So in other words, in geometric distribution, if you get the success at the X trial, it means that X minus 1 trials should be failures. Okay, so there's only one, and this should be success. So there's only one place that success is going to be observed when you're asking for what is the number of trials to get first success. It means that if you're looking for the probability to get the first success in 10 trials, okay, if you're asking for what is the probability to get this first success in 10 trials, it means that you get 9 failures. What is the probability to get 9 failures and get a success at the 10th trial? Okay, so 9 failures. The fails can go until infinite. So that's what it's saying. So it's this probability, the probability. So this Q to the infinity when the Q is non-zero. But here what it's going to do is it's going to go to 0. The probability is going to go to 0. Its limit is 0 because when this Q is a number between 0 and 1, as Q to the X, for example, if this is X minus 1 and this is P, this is going to go to 0 as X goes to infinity. That's for sure. But here, the success probability, the Q and 1 minus P, they are both non-zero. Their values, for example, P is 0.3, this one is 0.7. So they are inverse of each other, but they are values between 0 and 1. So as X goes to infinity, this probability is going to go to 0, but only at infinity. It's still non-zero. If you multiply 0.7 a lot number of times, what you get at the end is still non-zero. But this is what it's saying. X can go all the way to infinity, and we still have. So it's the probability mass function is something like this. It will start at P, right? So the first probability to get the first success is equal to P. So I have P here. Then it's going to start decreasing. Decreasing 1, 2, 3, 4, 5. It will decrease 1, 2, 3, 4, 5. And it's going to be very close to 0. It will be practically 0 maybe after 10 or 15, depending on what this P is. But it will never be exactly 0. It's going to be a decreasing function like this. Okay, so this is what the PMF looks like. and we can draw this plot all the way to infinity as long as your precision allows. But at some point, when you think about things like 10 to the minus 300, you'll see that I cannot even indicate a number closer to 0 smaller than this one. So my precision doesn't allow this. So let's call them 0 afterwards. And this is going to be your limit. But mathematically, you can go all the way to infinity. But practically, after certain trials, you're going to drop to 0. Yeah, actually, depends on. Oh, actually, let's see. A very good question. Does it mean that this is the success at the first is more likely? This is actually not true, right? Because actually, I drew this in an incorrect way, thinking that p this may be true when p is greater than 0.5. All right. What if, for example, p is 0.1? When p is 0.1, the graph is not going to look like this at all. It will first start with small probabilities, because the probability, if the probability of success is 0.1, you have only 1 in a 10 chance to get the success in the first trial. Okay, so the expected value of this is going to be, so the graph is more going to be like this, where its center of mass is at 10. So it's not always going to, so yeah, exactly. The second win is going to be equal to the probability of obtaining it at exactly at the second is this. But yeah, it's since we're always multiplying numbers, so it's going to be 0.9 times. So it's always going to be decreasing, right? Yeah, you're right. So yeah, it may be true. So it's always at the beginning. But when we think about the probability mass function, its expected value. So let's take a look at so the probability to obtain success at the 10th trial. We are always multiplying numbers with each other. P times this, P times Q to the power X minus 1. It's always getting smaller, right, as we are multiplying these things. So yeah, it's going to be decreasing, exactly. So it's a good observation. I thought it's going to be like that. Even okay. So the good thing is that in order for the center of mass to be at 10, for example, for 0.1, by the way, for geometric distribution, the expected number of trials to get the first success is equal to 1 over p. Okay, so you can, it's intuitive also. For example, if the success probability is 0.1, if you try 10 times, you expect to get a success at 10 and somewhere around 10. If the success probability is 0.1, which means one success in every 10 things. This is what 10% means, 1 in 1/10. If this is your success probability, you would expect it to be around 10, but the PMF function is not going to look like this. You're right. Since we're always multiplying numbers that are smaller than 1, it's always going to be increasing like this. That's a very good observation. And here, the thing is that even when we have a function like this, its center of mass is not here, right? If you think about this as a continuous block of wood, its center of mass is what the place where we have the number of probability 0.5 here, the probability of area under the curve 0.5 here is where the center of mass is. So it's going to be decreasing like this in the case of PMS, and when p is equal to 0.1, this center of mass is going to be around at 10. Okay, so which means that up until 10, you're going to have the entire probability space of 0 to 1. 0.5 is going to be fit into this area between 1 and 10, and all the remaining 0.5 is going to be distributed all the way from 10 to infinity. Okay, so it's going to be decreasing like this. So in that case, geometric distribution is going to look like the discrete case of exponential distribution. So because they are related. We are going to talk about continuous distributions where exponential distribution is like for waiting times. What is the waiting time until the next customer arrives? What is the next waiting time until the next uh, hardware failure occurs? So that's continuous. And geometric in that sense is like, what is the number of trials until next success? What is the number of trials until next success? It's like this the number of trials, and you see that it's going to look, its distribution PMF is going to very look like an exponential distribution, which is like decreasing like this. But thank you, and it was a very good observation. So if you look at this again, the PMF, so this is the PMF, and we can also check that the summation from 1 to infinity, this one, p minus 1 minus p to the x minus 1, this is a geometric series which is always decreasing. So it starts at some value and it's always going to be decreasing. This geometric series mathematically adds up to 1. So this is really a probability distribution function. And its expected value is 1 over p. As I said, if the success probability is p, 1 over p is the expected value of the number of trials. And its variance, we can also compute this by finding what is the expected value of x squared, and then subtract from it 1 minus p squared. You're going to get what the variance is. How do we find what is the variance of x? We need to again compute, in that case, in order to find the expected value of x squared, we need to compute actually a summation, an infinite summation. For example, in order to compute this 1 over p, we need to, let me refer to the book for that. We need to compute an infinite series. So this is what probability distribution is. So in order to compute expected value, let me zoom in here. Look at the expected value. Expected value is this, now we're computing a summation, but this is an infinite series. X times q to the power x minus 1 p. So this is the PMF x, and we sum all these x's weighted by their probabilities. And since the number of x's in this summation is infinite, we have to solve this infinite series. So you have to refer to your mathematics books to find how do we solve these geometric series. And it turns out to be this one, 1 times p over 1 minus q squared. 1 minus q is already p, so it's p divided by p squared, which turns out to be 1 over p. So similarly, we have to find the variance. And when we do the variance, we have to find the expected value of x squared. So x squared multiplied by this thing should be found. And then when we do that, when we subtract it from 1 minus p squared, which is the square of the expected value of x, we get our variance, which is like this. You don't need to memorize any of these formulas, I repeat. We are going to give that to you in the exam. So it's going to be available, these expected values and variances. So one example about geometric distribution is an interesting paradox. It's not a paradox, but when you think about it, it seems like a paradox, but mathematically it's not a paradox. This is it's called the St. Petersburg paradox, which is a strategy to allow any gambler to win eventually the desired amount. Okay, so if depending on what your success probability is, it may be 0.1, 0.05. This is a guaranteed winning strategy. Okay, and so even when the p is, let me just describe this to you and describe the paradox and what it's going to be. So imagine you're playing a game where you're just betting some money, so it's a gambling basically. So if I don't know the name of the strategy. This is the first time I heard martingale strategy. So it's the person who actually first found this is, if I remember correctly, it wasn't martingale. it was, if we go ahead and, so it's the nephew, it's actually the mathematician Daniel Bernoulli, Swiss mathematician Daniel Bernoulli noticed this paradox. Maybe it's that, yeah, doubling bet amount every lose. Exactly, it's that same strategy. Maybe Martingale found the strategy before Daniel Bernoulli, but this is how they figure it out mathematically. It's a paradox. So imagine you're winning, probability 0.05, okay? So the expected value of the number of trials. So you're going to win probably at in 20 trials, around 20 trials, maybe less, maybe 19, maybe 18, maybe 20, maybe 25, maybe 30, okay? But with the expected trial number of 20, which is 1 over 0.05, you are going to, that's going to be your first win, right? So imagine you want to win, for example, $100. So, but in order to be able to, so this strategy you're going to see is actually, in order to play with this strategy, you have to be really rich in the first place, because you are going to see that in order to win $100, you'll have to bet a lot of amounts. So you bet $100. So if your goal is to win $100 at the end, this is a guaranteed strategy to win $100 at the end. But imagine you bet $100 and you lose. Okay, the second time you try, you bet $200. You lose again. Now this time you bet $300. Okay, so if you win, actually it's going to be, so it was, let's see, is it going to be 400 this time? So we lost 300 up to now, so it's going to be 400. Okay, so every time you're betting, what you're doing is, whatever you lost here, you put plus 100 here and you bet at that amount. So, and here you are going to be betting $1,600, $3,200. So you see how this is increasing exponentially. Yeah, you may be. This the thing is that in real life, there is a limit about the maximum bet. Okay, so you cannot actually go all the way. You cannot always increase in real life. That's maybe one of the reasons the real gambling places actually put a limit to your gambling amount. There is an upper limit. You cannot bet more than this amount. If that's the case, I mean, this strategy is going to work if you always double what you have. Whatever you lost, you add 100 to that and you bet that amount. And at some point, this one says that the expected number of trials to get the first success is something finite, right? It's 20, which means that at some point you're expected to win. And the point that you win, you're going to be plus $100. Okay, so you have just $100. Okay, this isn't a paradox. I mean, this strategy isn't a paradox by itself. Okay, we are expected to win at some point. If you double the amount of, you're going to get $100 at the end. What makes this, yeah, what makes this a paradox is that although the number of trials is a finite number, if you try to figure out what is the sum of, if you define a random variable y, which tells that every time you're betting this amount, and this random variable y should indicate the amount of money, the total sum of money you have to bet until the first success. Okay, it's not the number of trials, but with this strategy, we are now defining a new random variable y, which is the amount of money that we have to bet until the first win. The expected value of this random variable is infinite. That's the paradox. So we have something finite, okay? mathematically it's finite, whatever it is, for example, it may be 2 to the power 20. Okay, if it's exponential, okay, exponential doesn't matter. I can just put it as an exponential number, and it should be still a finite number, right? But that's not the case. If you solve this, when someone is increasing linearly one by one, the other is increasing exponentially. If you find its expected value mathematically, and you look at the series and solve that series, the expected value turns out to be infinite when p is less than or equal to 0.5. It's going to be not infinite only if the winning strategy is, the success probability is greater than 0.5. So you will get, when success probability is greater than 0.5, you will get another geometric series, and this summed amount is going to be a finite number. But if your success probability is less than or equal to 0.5, although the number of trials, your expected value of a geometric distribution, is finite, 20 in this case. 20 is a really small number, right? But the amount of money you have to bet, the expected amount of money you have to bet to get the first win, is going to turn out to be infinite. So you have to be infinitely rich to win $100, which doesn't make sense. Okay, so that's which means that if in order to be infinitely rich, it means that why do you want to earn another $100? Infinite plus 100 is also infinite, so it doesn't make sense. I think that makes it also another way to look at this paradox. All right, so that's our paradox. And so here, this is the expected value of the sum of the amount that you're going to bet is going to be d times 2 to the power x minus 1, where x is our number of trials expected. Number of trials random variable is our geometric variable. X is our geometric variable. Y is this sum. And y is going to be, as I said, the expected value of the sum of money we need is going to be infinity when success probability is 0.5. So that's even if when you're playing with a single coin toss, heads or tails, and you want to win with just coin tosses, and it's a fair coin, the amount of money, even in that case, the expected amount of money you need is infinity. Okay, so that's the geometric distribution example. The negative binomial distribution, as I said, it's a generalization of geometric distribution. It's like between every successes, it's like a summation of geometric variables. If you're going to get, for example, 5 successes, if you want to win 5 times, you have to do trials until the first success, then another trials until the second success, another number of trials until the third success, and the number of trials between each successes is a geometric variable, which means that the negative binomial distribution is actually a summation of a number of geometric variables, because it's like we are summing up. If you're looking at the total number of trials, and the total number of trials is a summation of geometric variables that are until some success. So it's also, I think it should have been named as the inverse of the binomial. Here we fix the number of successes and count the number of trials until we reach that many successes. So it has 2 inputs, k, which is the number of successes. In geometric distribution, this k is 1. Okay, so this is a generalization of geometric distribution. Yeah, it's actually written right under in the last bullet. So in this case, the success is actually the first k-1 successes could occur anywhere. Now we have the degree of freedom to put those first k-1 successes anywhere. But the kth success, the last success, is going to occur at the last trial. So this is like, since the last trial is going to be a success, in the previous x-1 trials, the last trial is the xth trial when we are looking for this PMS. In the first x-1 trials, the possible ways you can distribute those k-1 trials is our degree of freedom on how to put those. All these probabilities are going to contribute to obtain the kth success at X, right? I mean, for example, if I want to get 5 successes in 50 trials, you should look at the probabilities where you get the first 4 successes in the first 4 tries, or the 4 successes in the 10th, 15th, 20th, 25th try. So those 4 successes could be distributed anywhere until 49, okay? But 50th one is going to be a success. So here the probability of obtaining x minus k failures, k successes here, this is the total. We have k successes, x minus k failures in k trials, in x trials, sorry. K is the number of successes. And if you look at the expected value and variance, since it's a summation of independent geometric random variables, the expected value and variance is very similar to what we had in geometric, only multiplied by k. Here, let's look at example 3.21. Probably I will start talking about Poisson on the first hour on Thursday, but it's not so a big deal. You don't want to rush. The quiz is going to be about chapter 3 or only. So if we just finish chapter 3 on Thursday, that's also fine. We're not too behind other sections. But let's look at this example that I'm going to finish today. So example 3.21. So let's go ahead and take a look at that. Negative 3.21. Sequential testing. So let's read this. In a recent production, 5% of certain electronic components are defective. Okay, so you're going to need to get used to these kind of examples in the book. It's always electronic components failures, something about computers. So this is statistics and probability for computer scientists, right? So we have all the examples are about electronics, computing. So I don't see actually doesn't make it, just making the example story about computers doesn't make it statistics or probabilities for computer science, but still it may some of the stories may be interesting. So 5% of certain electronic components are defective. We need to find 12 non-defective components for our 12 new computers. Okay, so our goal is to find 12 non-defective components. We're not looking for defective components. Components are tested until 12 non-defective ones are found. So here our success rate actually is 0.95, right? Success probability is 0.95, and we're looking for the k is equal to 12 here. And what is the probability that more than 5 components will have to be tested? So we are looking at a probability which is like the 1 minus the CDF. So in order to, the probability that more than 5 components will have to be tested can be, what is the probability get we have 12 successes in 15 tries, okay? So if you get 12 successes in 15 tries, and 15 or less tries, 12 successes in 15 or less tries, it means that it's the probability of to make 15 or less components, okay? Here, first of all, the probability to get 12 non-defective ones in just 11 tests is impossible. The value, that's going to be 0. So all the probability, that cumulative probability distribution from 1 to 11, it's going to be 0, because you can get 12 successes in at least 12 tries. So if you get 14 successes, and there are different ways to do this, to solve this question, but what I'm trying to solve is that find the probability to get 12 non-defective ones in 14 or less tries. That's really a negative binomial distribution. If you look at the CDF of negative binomial with 14 or less, and 1 minus that probability will tell you that more than 15 or more components have to be tested. But it's not saying 15 or more, it's just saying more than 15. So we should include 15 in our case. So we need to actually find out what is the probability to obtain 12 non-defective ones in 15 or less. So we need to look at the CDF of 15, okay, because we're asked here the probability that the number of trials is greater than 15. So we can actually find this by looking at 1 minus F15, where this F is the negative binomial. We are going to look at the negative binomial table with success rate of 0.95 and K is equal to 12, okay? But there is no table of negative binomial distribution in the appendix, okay? So that's a bummer. So we don't, where's the table? So we can use Octave Online to see whether Octave Online or MATLAB has negative binomial distribution. But we can solve it also another way. We can convert this probability to something else. So here the probability, so this is the interesting part of this example. Actually, if the example was just about negative binomial, this solution would be sufficient. And in the exam, for example, we would ask you sometimes just to leave your solutions like this. Just refer to the CDF or the PDF, whatever it is, just and leave the function like this by writing the subscripts correctly. So which CDF is this is one thing that we should know, which is I wrote somewhere here. Where was it? Oh, it was in the annotation of one of the slides, not on GIMP. So when you write the subscript saying that it's the CDF of negative binomial where K is equal to 12 and success probability is 0.95. So you have to indicate those values in the subscript correctly and refer to the CDF like this. That will be a correct solution and you may leave it at that. But practically, if you want to know the probability as some real number, we can also convert it to we can change the random variable to something else. Let's see how it did that. The probability, so this was more than 4 trials are needed to get the 12 successes, which means that 15 trials are not sufficient. So in order to, so 15 trials are not sufficient because you need more than 15 trials. It means that there are fewer than 12 successes in 15 trials. We now, at this point, look at the sentence here. Now, when you fix the trials, what is the probability to obtain less than 12 successes in 15 trials? What is this random variable y? I mean, if you look at this random variable y, what is the probability that y is less than 12? Y is now the number of successes. The probability that number of successes is less than 12 in 15 trials. It's exactly the same probability. By just rewording what we were asked, it became a binomial variable, right? We not fixed the number of trials, fixed 15 trials. The probability to obtain less than 12 successes in 15 trials becomes the probability that you're looking for. So here, by changing, that may be one of the reasons why it's called negative binomial. If you're asking a negative binomial question, we can always convert the random variable to a binomial one, depending on what we are asked in the question in terms of probability. This probability 15 can be a parameter to our binomial distribution. In 15 trials, what is the probability to get less than 12 successes? If you get 12 successes in 15 trials, this is not the probability you're looking for. The probability to obtain less than 12 successes, the probability to obtain less than 12 successes in 15 trials is the CDF of binomial. N is equal to 15, P is equal to 0.5. If you look at the CDF of this, it turns out to be this number, 0.0055. Okay, so this was an example to convert one random variable to another one by changing the English wording and seeing that, these are the same probabilities that we're looking for. Okay, so you may need maybe more time to understand how we did this, but it may be also very clear in the first case. So just if it's not immediately clear, please take your time. You may read the example again and try to understand it on paper. draw some figures, what is going on, the number of trials, the number of successes, and I'm sure you're going to get correctly if you give it enough time. All right, so now we're at Poisson distribution. I already mentioned what Poisson is. It's the average number of events that occur in a fixed amount of time, and we are going to talk about the details of Poisson distributions on Thursday. I'm going to stop the recording now,